Assalamualaikum warahmatullahi wabarakatuh. Uh, Today I'm going to continue our lectures on work and energy topics. So today we are going to discuss on principle of work and energy. So there's a bit, ignore this one. There are some mistake here. Principle of work and energy, right? Okay, by applying the principle of work and energy to each of the particles of a rigid body and adding the result algebraically, since energy is a scalar, the principle of work and energy for a rigid body becomes T1 plus summation of work done from 1 to 2 is equal to the kinetic energy at point 2. So let's say it start from point here. Let's say this ball uh, roll from point 1 to point 2. So the kinetic energy at point 1, eh, okay, and then you have kinetic energy at point 2. Okay. Kinetic energy at point 1 plus the work done from point 1 to point 2 is equal to kinetic energy at point. Right, the work done. We have discussed on work before. You have uh, you have what we call it work of force, work of a weight, work of a spring force, and then we have work of a couple moment. Huh? That's in summation of work from 1 to point 2. Okay, that's the principle of work and energy. Everything on uh, kinetic energy at point 1 is on your left hand side plus the work done is also on left hand side. And only the kinetic energy comes at point 2 is on your right hand side or right of the equation. Okay, that's the principle of work and energy. But the thing is, we have to understand more about this. We have to discuss on by taking one example. If you refer to our textbook on page 464, uh, example 18.2, right? The 30 kilogram disc shown is pin supported at its center. Okay, determine the number of revolutions. How many times it rotates. I means that it must take to attain an angular velocity of 20 radian per second. This is the final one. This is point two. Okay, starting from rest is at the beginning lah. Point one. It is acted upon us by a constant force, F is 10 Newton, which is applied to a cord wrapped around its periphery, and a constant couple moment, M, is 5 Newton meter. Okay, okay. So what should we do? Eh? As we have done in force and acceleration, we have basically draw the FBD. From the FBD, we know what is the force acted on the rigid body. Here we have external moment, 5 Newton meter, and we have external force here, 10 Newton. And also, since this is a pin here in the middle, we have, for the example, OY. Okay, and then we have OX. This is the force acted on this rigid body. And then you have the weight, you have the weight as well, weight, weight, downward. And G, where is the G basically? This is the, we see that, of course, G is in the middle for this kind of symmetrical rigid body. G is in the middle. G and O is at the same point. Okay. Then what should we do? So basically, from the principle of work and energy, we have T1 plus the work done from 1 to 2 is C1. So it's T2. So we start from rest. Okay, basically, but before that, what is T1? T1 is come from here, half mvg square, right? Plus half I G omega square. Since G is in the middle, eh, instead the point G or point O doesn't move left and right, and so on. It stick there. So Vg is 0. This term is 0 because V, there's no V, but we still have omega. Okay, and Ig is the mass moment of inertia. Alright. Um, Similar to T2 is half mvg square. So this one is 0. Do we have this element? Yes, because it achieves omega 20 radian per second. Okay, this is one. But at 1, it starts from rest. Okay, so omega 1 is also 0. Alright, so what we can say is T1 is 0, T2 is 1 over 2, Ig omega 2 20, because omega is 20 radian per second. Okay, so the work done 1 2 2 is what? The work done first, we have OX and OY. Since this work doesn't create any displacement, so it doesn't create any work, right? So what left? The only M, external couple moment, and external force. Okay, so the work done first, the work done by moment 5 Newton. So work done by moment is U moment basically is M times theta. Alright, M is 5 Newton, theta 1, sorry, theta 2, theta 1 lah. So it start from rest, theta 1 is 0, theta 2 is unknown lah. So theta 2 for example, positive okay, positive. And then the work done by the what we call it, the force is also 5, sorry, 10 Newton. Time is radius, you got the moment, correct? It is 0.2. And then also you times theta 2 minus theta 1 lah. So theta 1 is 0, so left only theta 2. Okay, you can arrange the equation of the principle of work and energy here by 0, T1 is 0 plus 5 theta 2, okay, then plus 10 times 0.2 times theta 2 is equal to, right, what is the T2? T2 is half Ig omega 20 times 20 to the power of 2. So what is Ig for this this Ig for this is 1 over 2 m r square. So half over 2 times 30, r is 0.2 square. Right, so the answer here is basically, I'm not really sure, but you can put here, but the answer here is 120 lah, so T2 basically 120 joule. Then what left here? The only unknown here is theta 2. So your theta 2, basically the answer for theta 2 is 17 point. The answer from this calculation, basically the answer is in radian, 17.14 radian. But this is a radian, but the question is you have to find the revolution. And the revolution, we know that 2 pi radian is equal to 1 revolution. If we have 17.14 radian, so how many revolution? if you divide it by 2 pi, here you by, this is the just we call it uh, right. So you have what? So means that 17.4, sorry, 17.14 radian divided by 2 pi radian, you got the number of revolution is equal to 2.73 revolution. So from 0 radian per second until 20 radian per second, it's rotate for 2.73 revolution. Okay, that's the answers for this very simple question. In this problem, you have only a rotational about fixed axis. Rotational about a fixed axis. Okay, so we continue to the second example. Second example in the same video. On the same video. All right, we have wheels with 20 kilograms and has a radius of gyration 0.18 meter about its mass center G. It's mentioned to you is the kg is about the center. If it is subjected to a clockwise couple moment of 20 Newton meter and rolls from rest without sleeping. Take note that it's roll without sleeping. When it's roll without sleeping, we know that the IC is there. A roll without sleeping, so you can use uh, alpha. Sorry, A is R alpha, and you can use a V is R omega. You cannot use we cannot use this one anymore. F is mu K, and you cannot use this one. Okay, determine the angular velocity omega. Okay, after its center move 1.0.15. After it move 1015, sorry, it's not 0.1 meter and 0.1 meter. Okay, the spring stiffness is 100. Okay, a bit sorry. Okay, stiffness 160 and is initially unstretched when the couple moment is applied. Okay, I want to do a correction bit. Wait a minute. Okay, there are some correction. The weight remain 20 kilogram. Radius of gyration is kg is 0.115. The couple moment is 20 Newton meter. The spring stiffness is 200 Newton meter per meter, and the point G, center G, move 0.1 meter from rest without sleeping. Okay, so this is the FBD. This is the FBD, and then because this is a kinetic diagram lah. So you have the spring force there. The displacement is on the right of the spring, and then of course the opposite, the force is opposite from the displacement. You have a normal force and B, straight friction force FB. Okay, you have weight here, you have weight, and then you have couple moment, right? So basically we have what? T1 is normal one. T1 plus summation of force, sorry, work from 1 to 2 is equal to 2 T2. So T1 basically the kinetic energy at rest. So roll from rest. So both element T1 half mvg square plus half ig alpha is equal 0. We'll start from rest lah. Okay. And then we have T2 plus T2 kinetic energy at point 2 after G displays for about 0.1 meter. So T2, we can say that half mvg square plus, okay, this is a linear translation. G move from this point to this point. Okay, then this is the kinetic energy to the rotational motion, half ig omega 2 square. And then we know that since this is IC, okay, Roll without sleeping, roll without sleeping. Rolls without sleeping. So this point is point IC. So when we know the point IC, we can determine the V of G. VG is equal to R omega and AG is R alpha. So instead of VG, you put R omega, half M R square omega 2 lah, plus half IG omega 2 square. Alright, so this is not zero because you have the values. And then the work done. First, the work done, I just put the work done by weight. Weight doesn't create any motion in downward and or upward. So weight is not counted. Similar to NB, is also not counted. But we have what? The work done by Fs, by the moment. And how about the FB? Right? The FB, for this case of row without sleeping, FB doesn't work since the wheel doesn't sleep as it roll. If it will roll without sleeping, FB is not counted in calculating the work because it doesn't create any force. Any works while it's rotate without sleeping. Okay, so only two elements, only two forces or moment counted to calculate the work done. F spring, moment. So I start with moment from point 1 to point 2, which is m times theta 2 minus theta 1. So its m is 220 Newton meter. Theta 2. Do we know theta 2? No, we don't have theta 2. So it's theta 2. Okay. Point G move from point 1 to point 2, for example, point 1 to point 2 for 0.1 meters. We know that V is R omega, A is R alpha, and D, the displacement, is R theta. So theta D is 0.1 meters, R is 0.24, and we have theta. Theta is 0.5 radian. Okay. So here is 0.5. We have the work done by the couple moment is 10. 10 joule. 10. Okay. Then we have the work done by the work done by the spring from point 1 to point 2. Do you remember this equation? S2 square minus K KS1 square, KS1 square. Alright. So minus half 200 S2. We do what is S2? We don't know. But what is S1? S1 is sorry, S1 is 0 lah. Since when it at rest, it is in unstretched position. It initially unstretched. Okay, so here is 0. But what is S2? S2 here, we see that as we discuss here, this is the IC. So any point on this rigid body, similar at the force acting at due to the spring here, this point, we can measure, we can calculate its velocity, we can calculate displacement and everything. Okay, so the displacement of the spring, this spring is equal to R times the radius from this point to IC. So means that a point spring to IC times omega sorry, not omega, times theta, times theta. So R, as I see, is to 0.24 times 2, 0.48, 0.8 times theta. Theta is 0.5. And then you have your answer for D. Yeah? The displacement of the spring is around uh, 0.2, 0.24 or 0.2 lah. In the textbook, written in 0.2. Doesn't matter lah. Whatever value you found, if you calculated, so you can use it lah. So the answer here is minus 1 divided by 2, 200, and S2 here is 0.24. Or we take it 0.2 lah to be similar with the textbooks. 0.2. And the work done by the spring is negative 4. Negative 4 joule. Then if you put everything in the equation for principle of work and energy, you can find that I rewrite the equation T1 plus the summation of work done from 1 to 2 is equal to T2 0, okay, plus 10 the work done by the moment, and then minus 4 the work done by the spring, and T2, what is T2? T2 is 0.6371 omega 2 square. And your answer here, if you calculate the omega is equal to 3.07 radian per second square. Easy class, huh? Okay, so I think that's the two example from principle of work and energy. And then I have one more basically example. I think I have to discuss in it still in the same video. Uh, uh, and I hope that these three example uh, can make uh, you understand more about the work principle of work and energy. Okay, so we are going to discuss the third equation, the third example. Okay, right. In this example, we have 10 kilogram rod is constrained so that its ends move along the groove slot. Both ends, and A and B, follow the slot. Can go up and down. Okay, this one can go left and right. Okay, the rod is initially at rest when theta is 0. This is theta. When theta is 0 means that the position of the rod is like this. This point A, this point. This is the theta is 0 at rest. So when at rest, Vg is 0, omega is also 0. That's the key point of rest. If the slider block at B is acted upon by a horizontal force P, okay, to the left, determine the angular velocity. You have to find omega, okay, at point 2 of the rod at the instant theta is equal to 45 degree. Alright, I have to, let's draw again. Let's say this is the initial position. Okay, initially it is at rest when theta is 0. So this is the groove slot B. So at one time it become like this, 45 degree. So basically this is your G at the beginning. Half of the length of the road. This one is 0.4. This one also 0.4 meters. Now G, when it displays for about 45 degrees, G is reduced. They say this is the level of G. Now the level of G here is somewhere here. This is your new G. Okay, the position of the new position of G. Now this is the new position of G. You can imagine that this is delta Y. Okay, and then one thing is the force given, external force given 50 Newton from rest until at point 2. And this is point 1. Okay, so you have to know the distance from point 2 to point 1 delta S. That's the most important thing. Because this external force create the motion. Alright, so basically we have T1 plus the work done by all forces or moment from 1 to 2 is equal to T1, of course 0 because Vg1 is 0, Vg2 is, sorry, omega 1 is also 0. So left only the work done by all the forces or moment if exists is equal to T2. Right. Okay, this position, initial position, theta is 0. This is theta 45 degree. Right, since this is a groove slot, it can move up and down. The velocity at this instant is downward. So this is a VA. Can go ups and down since this motion is clockwise. Clockwise. So this is a VB. Only one component of VB. Okay, if we draw X and Y, so we have a negative VA, we have a negative VA for the example, and we have negative VB. Okay, doesn't matter. Okay, so we have BVB here. You see, you have VA there downward. Since you have two direction of velocity on the same rigid body, you can draw what? You can draw the IC. Sorry, VA, VB. Okay, since you know the direction of 2 points of the velocity on the same rigid body, you can find the IC. You draw the 45 degree from this point, also 45 degree from point B. So this is I point IC. So if you know the point the point IC, you can calculate all the velocity on this rigid body. Let's say you have G here. You can calculate the VG. Draw the straight line from IC to G, and this is a VG. Let's say you have another point here, you want to calculate this point, draw a straight line from IC to that point, draw a 95, 45, 95, 90 degrees here. This is the V for this point. Okay. Now, we see that first from the previous figures. Okay, we have weight, changing from this point to this point. So we have work done by the weight. The work done by the weight is weight times delta y. And we have work done by P. So P times the distance delta. This is the two important work done by forces. And then, so if we calculate the work done by the weight is W. What is W? W is figure here. Okay, the weight is 10 kilogram. The W is 10 times 9.81 delta Y. What is delta Y? Okay, delta Y. Initially, if I draw it here, initially it's like this, 1.4. And when it displays for 45 degree, okay, this is the new position of G. And this is when theta is 0, when this one is theta 45 degree. So you have to know the distance between these two, delta y, because you only know the delta y. So means that what you have to do is you delta y, and from this figure we can say the delta y is equal to what? 0.4, 0.4 minus the distance of this one. Because this one you can find it, right? Because this one is 0.4 and this one is 45 degree. So how to find this one? This distance, I put this theta y prime, delta y prime is equal to y prime is equal to 0.4 sine 40 sine 45. Okay, sine 45. Okay, and then delta y is equal to 0.4 minus delta y prime, which is 0.4 minus 0.4 sine 45 degrees. That's the delta W. Okay, sorry, the work done by the weight. How about the work done by the P? The work done by the P is equal to 50 Newton times delta S. So what is delta S? Delta S is from this point, as I drew it before. Yeah, from this point to this point. Okay, so means that this is here. How to calculate this one? Here is 45 degree. So to find the delta S, I put the delta S here is 0 0.8, 0 0.8, 0 0.8 times cos 45. Okay, get the delta S. So 50 times 0 0.8 cos cos 45. This is the work done by the P. The external force 50 Newton. So what we can write here, T1 is 0 plus, okay, delta Y, sorry, delta W, 10 times 9.81 times delta Y, which is 0.4 minus 0.4 sine 45, 0.4 sine 45 plus 50 times 0.8 cos 45, 0.8 cos 45. Then plus is sorry and equal to T2. Yeah? First you have rotational motion, and at the same time you have the translation of the point G, because G is moving, yeah, from here to here. Okay, so you have a half m cos G squared plus half Ig. So Vg, since we have the IC, we know that half T2 is half, m is 10 kilogram. Vg, you see that Vg is Rgic times omega 2. Okay, but what the distance here? The distance here is equal to 0.4. You have to calculate this one. So this one, since this one 45 degree, this one 90 degree, this one 45. So this length is equal with this length lah. Okay, so this one is 0.4. 0.4 square times omega 2 square plus half. What is the Ig? Ig for a road, road is 1 over 12, 1 over 12 m, ml square, ml square, ml square times omega 2 square, omega 2 lah, yeah. And then, yeah, after you solve this only unknown, one unknown here, which is omega 2. So once you solve this one, you can find that your omega is equal to 6.11 radian per second clockwise. Okay, that's the answer for this example. Alright, I think it's a very clear, straightforward question. I think it's not difficult for you to solve for work and energy. Right, using the principle for work and energy, principle of work and energy. Okay, so we still have one more subtopic, which is conservation of energy. For conservation of energy, I think it will take like another 1 hour of lectures or videos, and then we finish our topic. Okay, thank you very much. See you in the next video. Assalamualaikum warahmatullahi wabarakatuh.